Okay, this is the third section for chapter 9 called Hybrid Orbitals. And this is an excellent section because it kind of helps us understand a little bit more about how bonds work. And let me just give you an example here to start out. When you think about carbon, carbon is an atom that very commonly forms four bonds. Okay, very common molecule is methane. Another common one might be ethane, but you can see in both cases the carbon typically does form four bonds. So like in carbon dioxide, pretty much in most molecules, you'll find that carbon does form four bonds. Certainly an exception to that might be carbon monoxide where it only forms the three, but typically carbon is a molecule that forms four bonds. When we talk about hybrid orbitals, we're talking about where do these electrons actually come from to form the bonds. And when we think about carbon, if we look at the orbital diagram, carbon's 1s2, 2s2, 2p2. And so basically what happens here is you've got two free electrons. And so what we would predict based on this information is that carbon should only form two bonds. It should form a bond right here to pair that one up, and it should form another bond here to pair that one up. But from experimental data, we know that that doesn't happen. We know that carbon almost exclusively, but not always, does form four bonds. And so we know that this orbital diagram that we've got for carbon doesn't really work because we know a couple of things. We know that carbon typically forms four bonds, and we also know that these four bonds are equivalent. And what we mean by that is energy-wise, they're at the same level. Because if these 2s electrons down here were forming a bond, then these two bonds might be from here, and these two might be from here. But we know that the energy level of all four of those bonds are very similar. Therefore, there's a couple of problems with this. Number one, carbon only has two open electrons that can form a bond, and the four bonds that it does form are all energy equivalent. So we're going to, with using what are called hybrid orbitals, we're going to be able to solve both of those problems. So we're going to talk about hybridization. We're going to assign the types of hybridization based on the bonds that we see. So we know that electrons do overlap when they do form covalent bonds, but it's not always easy to see. So a hybrid orbital can occur when atomic orbitals on an atom mix to form new orbitals instead of just the traditional s, p, d, and f orbitals. The shapes are different as well as what we call them are different. So hybridization is really nothing more than the process of mixing and thereby changing the atomic orbitals as atoms approach each other to form bonds. But again, the real question is, why does hybridization occur, or why do hybrid orbitals form? And it comes right back to this thing right here. Because of this. Because if not, carbon can't form bonds. Carbon can form two bonds and that's it. But we know that that doesn't happen. So, consider the molecule BeF2. The Lewis structure for BeF2, BeF would look something like that. The orbital diagram for Be would be 1s2, 2s2, kind of like how we just did with carbon. According to this orbital diagram, beryllium has no unpaired electrons. Look at that right there. It has no unpaired electrons and therefore would not form bonds. But we know that beryllium does form bonds because we know that beryllium fluoride exists. So what we do is we're going to promote or raise up one of those 2s electrons to the 2p orbital. And then if it does, then it could form two bonds. Okay. So let's see. Go. So here's what happens. So normally what we've got, let's bag this part here. So beryllium is normally 1s2, 2s2. Okay, and then after beryllium, which we normally don't even write, you have this empty 2p orbital. What happens here is one of these electrons here, and it doesn't matter which one, gets promoted or raised to the next level to the 2p. So what you end up having now is beryllium 1s2, 2s1, 2p1. Now that solves one of our two problems. Remember that our two problems were they don't form enough bonds, or they don't have enough electrons to form that many bonds, and the energy levels are different. What we've just done is we've solved our first problem in that we've now got two available electrons for beryllium to bond with. The second problem, though, we haven't solved in that they're at different energy levels. This electron's at the 2s, this electron is at the 2p. So what we've got to do is we've got to have those energy levels at the same point. So here, between this step and this step, all we've done is promoted an electron. What we're going to do now is we're going to hybridize those orbitals, which means we're going to take that 2s and that 2p and we're going to put them together. So we're going to get what's called an sp hybrid orbital, and then you've still got those two empty ones that are the 2p. So we've taken an S and we've taken a P and we've put them together to form an sp hybrid orbital. And so we've still got these empty ones here that don't really have anything to do with the reaction at all. But now we have two electrons that are at the same energy level, and therefore their bonds will be equivalent. And we also have the free electrons for making that bond. Okay, so here you can kind of see that. Here it is the sp. They're both spinning the same direction, and then you've got those empty 2p ones over there. So those two electrons in the sp hybrid orbital are unpaired, and they can be used to form bonds with the fluorines. And although that promotion does require some energy, I mean, you're taking an electron from the 2s and you're moving it up to the 2p, these orbitals can overlap stronger now with these other orbitals, and stronger bonds result, which offsets that energy needed. Okay, now, so one type of hybrid orbital that we've discussed are sp hybrid orbitals. You can also have, this is not pronounced sp squared, this is called sp2. And in an sp2 hybrid orbital, you basically get this, where you've got something such as, this would be boron. Okay, boron would be, and they didn't put the 1s in there, it'd be 1s2, 2s2, 2p1. Okay, same thing, boron often forms three bonds. Here it looks like it only is going to form one. So this electron again is going to get promoted up to the 2p level. And so then we end up having 2s1, 2p2. Once we promote it, then we also have to hybridize it, which basically means we're going to take this and these and put them together, and we're going to leave this one empty 2p all by itself. Now, why is it called sp2? Is because we've taken one s orbital and two of the p suborbitals to make an sp2 hybrid orbital. This one was just called sp because we took the s orbital, the 2s, and one of the 2p, so this one and this one, and we put them together. So it's sp2 hybridized, and therefore now, number one, again, the energy levels are equivalent. Therefore, they can bond with other atoms at the same energy level, and it can form three bonds. Okay, what that actually looks like, this is what an sp2 hybrid orbital actually looks like. And you can see it looks just like a triangle, which is why we get that 120-degree bond angle, and that's why we call it a trigonal planar. Things that have three bonds and no non-bonding pairs form that shape. Okay, so we've got sp. That is a combination. Boy, what just happened here? Let's see here. Hold on here. Something's going on. Let me hold on. So in an sp hybrid orbital, we've got an s orbital and one of the p orbitals coming together. In an sp2 hybrid orbital, we've got an s orbital and two of the p orbitals coming together. So obviously in an sp3 hybrid orbital, we're basically going to have all four of them come together. So you can have a mixture of the three p orbitals and the one s orbital. For example, carbon, a very common thing with carbon is you'll see carbon, as we saw at the beginning, was 2s2, 2p2. So again, this electron's going to get promoted, and you've got that. Once that promotes, then they hybridize together, and you get an s with three p's, so you get sp3 hybridization. Okay, carbon can form four bonds. All of those bonds would be equivalent bonds, and that certainly helps us understand how something like carbon does form four bonds that are all equivalent to each other. So this is what it looks like. You can see that bond angle of 109.5. Obviously, that is a tetrahedral shape, and that's your 1s and the three s's, or the three p's, excuse me, all coming together. Okay, with d orbitals, you can get the same thing. Now, notice on your periodic table that boron to neon have no d orbital after them. Okay, d orbitals happen when you get expanded octets, when you get something like pf5 or sf6 or something like that. You would never see ch5 or ch6. You would never see of6. You would never see NBr6. Why? Because they don't have d orbitals after them that could form hybrid orbitals. After the 2p comes the 3s, then the 3p, then the 4s, then the 3d. So you'll notice that when things do form expanded octets, it's always something after carbon, nitrogen, oxygen, fluorine, basically all those elements in the second period. It starts with phosphorus. Phosphorus very commonly makes PF5 or PCl5. Sulfur, oftentimes SF6. And they do have hybrid orbitals, okay? And the way that that works is, again, just like the other ones, where we basically have phosphorus is 3s2, so phosphorus, 3s2, 3p3, 1, 2, 3. Now we know that following the periodic table, the next one would be 4s, but we know that energy-wise, the one that really comes next is 3d. Okay, so this electron here isn't going to come into one of these spots because there's no space for it. So what it does is that electron gets promoted all the way up to the d orbital. So you have an s, you've got the three p's, and you've got a d orbital. So this is called 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, an sp3d hybrid orbital. And then that d over here is just 4 empty d's. And then the final one that this can happen on is sulfur, or anything that could form another bond there. With sulfur, again, something somewhat similar here, where sulfur it starts as 3s2, 3p6, or excuse me, 3s2, 3p4, 1, 2, 3, 4. So in this case, this electron gets promoted up to here. This electron gets promoted up to here. Boom, boom. It's gone from here. It's gone from here. Now it needs to hybridize. sp3d2. 1, 2, 3, 4, 5, 6. Hopefully that helps you understand. Why does phosphorus normally form 5 bonds? Well, because when it hybridizes, it forms sp3d hybrid orbitals. Why does sulfur tend to form 6 bonds? Because it's sp3d2 hybridized. Okay, and other elements in that those same periods below, or that same family below phosphorus, arsenic tends to form 5 bonds as well. Nitrogen above phosphorus does not. Again, because there's no d orbital after it. Sulfur, 6 bonds. Selenium, 6 bonds. Oxygen, never 6 bonds. Again, no d orbital. So that just kind of shows you what they look like there. You've got the sp all the way down to sp3d2. And basically, these are the shapes that we've already seen. When we were doing shapes that last section, or a couple sections ago, these are our shapes. Here's our linear shape. Here's our trigonoplanar. Here's all of the shapes that we already know, and they're all based on hybrid orbitals. Okay, so we can use this for non-bonding electrons as well. If we think about water, water has 2 bonding pairs and 2 non-bonding pairs around the oxygen. So you got HOH, boom, 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 making it a tetrahedral shape. The 4 electron pairs can be envisioned as occupying sp3 hybrid orbitals. Okay, and how might you look at that? Oxygen is normally, let's see, oxygen is 1s2, 2s2, 2p, 1, 2, 3, 4, 1, 2, 3, 4. Now in this case, we do not have to hybridize anything. Excuse me, I said that wrong. We do not have to promote anything, but we do need to hybridize. And the reason that we need to hybridize is because these electrons here are at a different energy level than those ones. With water, we can see that hydrogen comes in here and forms that bond right there, and the other one forms the bond right there. So here's our 2 bonding pairs. Here are our 2 non-bonding pairs, but again, we know that those are equivalent. Therefore, this one and that one have to come together. So you've still got 1s2, and then you've got sp3, 1, 2, 3, 4 are non-bonding, and then these are the ones that form the bond with the hydrogens. And they're all at the same energy level, therefore making the bonds and the non-bonding pairs equivalent in terms of energy. Now, having said all that, summary, let's look at that. Easiest way to determine hybridization, draw the Lewis structure. Determine the shape based on the Vesper model. Specify the hybrid orbitals needed, looking at the bonds and the non-bonding pairs. Now, what that means is it's usually really simple. With a molecule, you count the bonds, and again, the single bonds, the double bonds, and the triple bonds all count as one bond. So whether it's single, double, or triple, that counts as one. You count the bonds and you count the non-bonding pairs. You add them up. And it's either sp or all the way up to sp3d2. So if you have 2 bonds and 2 non-bonding pairs, that's a total of 4. So basically you would get to 4. You'd go s, p, p, p. That's 4 things. It's sp3. Okay? So let's look at these. NH2 minus. NH2 minus would have 5, 6, 7, 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Here you've got 2 bonding pairs. You've got 2 non-bonding pairs. Therefore, overall, you've got 4 electron domains, making it sp3 hybridized. Okay. SF4, also very similar. You've got 34 electrons all total. So you've got 1, 2, 3, 4 bonds. Put all our dots in here. We've got 32 electrons here. We've got to use all 34. There's 34. So again, let's count these up. 1, 2, 3, 4, 5 goes S, P, 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 D. 1, 2, 3, 4, 5. This is sp3d hybridized. Now you might be thinking, well, why didn't you just tell us at the beginning? Why did you go through all that explanation? Because I think it's kind of cool and it's fun to learn why it actually is sp3d hybridized. SO32 minus would have 26 electrons. SOOO. So here's our 24. We've got 2 left over. That makes 26. 1, 1, 2, 3, 4. SPPP means sp3. And then our last one, SCl6, would have 6 bonds, no non-bonding pairs, so it'd be SPPPDD, 1, 2, 3, 4, 5, 6, sp3D2. Okay, so there's our answers there. You see those. Obviously, this is a big portion of this packet. They are pretty quick though, so I gave you just a few out of the book here for you to do. And again, please take a look at these. Like I said, they don't take very long. Just look at them, figure out the bonds, figure out the non-bonding pairs, and then you'll have your hybridization.